In the previous example, we looked at the limit as x approaches 0 of 5 over x, and the graph looked something like this. And when we tried to figure out what was going on with this function as x got closer and closer to 0, we noticed that the behavior of the graph was different on either side. On the left side, this function seemed to decrease or get smaller without bound, and the other one seemed to increase without bound. So kind of different behaviors on each side, which leads us to an idea that we may be interested from time to time in talking about the limit of a function from just one side of a certain x value. And that's where we have something called one-sided limits. And so the notation for one-sided limits is here in the middle of the page. You can see the limit as f of x approaches as x approaches c, and then there's a little plus sign there in the top corner. That means from the right. And then left-hand sided limits, you can see the limit as x approaches c with a little minus sign on the in the exponent, and that means approaches c from the left. So now we have a notation and an idea about how we can talk about limits from just one side. And so one nice way to visualize this is in something called the greatest integer function. Greatest integer. It's also called the floor function. If you've ever heard of that before, it's often signified sometimes with like double brackets. Sometimes it's got kind of just a bottom portion. And the graph tends to look something like this. It's almost like a set of stairs. Maybe you saw that sometime in pre-calc or intro to calc there. So this is called the greatest integer function. And what it does is it kind of takes all the values, say for instance, this is 1, this is 2, takes 1.1, 1.2, 1.3, 4, 5, 6, 7, 8, 9, and kind of cuts off that decimal and rounds it down to 1. So for instance, the greatest integer of 1.9 is 1. All right, so what if I asked you then on this particular function, what is the limit as x approaches 1 from the left of that greatest integer? So let's see. If we approach 1 from the left side, this function is flat and it's tending toward a y value of 0. But if we ask the same question, but now change this as limit goes to 1 from the right of the greatest integer, well, let's take a look at the graph. As we go to 1 from the right side of the graph, we're flat again, but we're tending toward a different y value, this time the y value of 1. And so we can see that there are functions that have different behaviors from either side of a certain x value. And now with one-sided limits, we can evaluate or examine those different behaviors. So if we've got one-sided limits, then we must have two-sided limits as well, and it turns out we do. We sometimes call this generic limit form here, where we don't have the exponential plus or minus, the two-sided limit of f, to distinguish it from a from a right side or left side limit, or right hand or left hand limits. So this is super important here. It probably should be in its own space and pointed out as a big theorem. A function f of x has a limit as x approaches c if and only if the right hand and left hand limits at c exist and are equal. In symbols, the limit as x approaches c of f of x is equal to L. The limit exists and is some number if and only if the right hand limit and the left hand limit are the same value, and they also must exist. So that's going to be a way that we use to examine something called continuity here in a little while. But for right now, that is an existence of a two-sided limit theorem. Here is one example that we can use to see one-sided limits. Answers are in there, but maybe we can just confirm them. Here's a graph of f of x, and we can see it's a piecewise function. Part A, what is the limit as x approaches 0 from the right? Well, let's see. Here's 0. As we approach from the right, it seems that the graph is headed toward a y value of 0, and that's what we have here. What about the limit as x approaches 2 from the right? Well, here's x equals 2, but there's not a graph to the right of 2. There's nothing there. So in that case, we really can't approach 2 from the right, and that means our limit does not exist. Okay, next question. What is the limit as we approach 2, this time from the left? So here's 2. Let's approach from the left. And we seem to be headed toward a y value of 4. And then the next one, part D, this doesn't have a plus or minus. So part D is what we refer to as the two-sided limit. And in a two-sided limit, we know now, thanks to the previous theorem, that the right side and left side limit, or right hand and left hand limit, must both exist and be the same thing. And in this case, they're not. The left-sided or the right-sided limit does not exist. The left-sided limit was 4, so we have to say this one does not exist. Finally, what's the limit as x approaches 3 from the right? Well, check out the graph. We are headed toward a y value of 0. All right, last part of this lesson is something called the squeeze theorem, and it goes like this. If we cannot find a limit directly, and we're going to run into those situations, we might be able to find it indirectly with the squeeze theorem. This theorem refers to a function f whose values are squeezed between the values of two other functions, g and h. And if g and h have the same limit as x approaches c, then f has that limit too. It's going to look something like this. Say we have some function, and we're wondering what happens to this function at some x value. We're going to call it c for constant, but we can't find it. We can't do any sort of algebra analytics. We can't use any sort of method that we know about to find the limit, but we are able to somehow squeeze that function between some function that is always above, we're going to call that one g, and some function that is always below, we'll call that function h. Well, if I know that this limit can be found, and I know that this limit can be found, and if those two limits are the same, well, then f of x has that same limit. So let's see that in the theorem. If g of x is less than or equal to f of x, which is less than or equal to h of x, in other words, f is between g and h for all x not equal to c in some interval about c, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x, and both of those are equal to the same thing, same limit, then the function f, that again, remember, it lives between g and h, is equal to L. I'm going to take a look at this one more time, guys. So if we have some function g, and it lives in an interval containing c, and we have some function h, and it lives in the interval containing c, and both of those have the same limit. And if we can squeeze our function in between them, well, then our function f has the very same limit. And so here's an example of the squeeze theorem in action. Show that the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. So if we say that the function f is x squared times the sine of 1 over x, and there's no way to find that limit on our own, what we can do is find a limit that, or find a function that lives above it, find a function that lives below it, and squeeze f in between those two. And the work below shows how that can be done. It uses a function negative x squared. It uses a function x squared. Both of those are equal to 0. And because negative x squared lives below and x squared lives above this function, then we have the limit as of x squared times sine of 1 over x equal to 0. So there we have it. Here it is in graphical form. I think this is a much better way of putting it. So this function is y equals x squared. This function is y equals negative x squared. And the blue function is our f, which is this function here. And see how it gets squeezed between those two functions. And since the limit of negative x squared and the limit of positive x squared are both 0, then we have the limit of f being 0 as well. And that's everything for 1.1.